Swayam Prabha. Digital India. Educated India.
So, we will carry on with the discussion on the hydrophobic effect, and what we were I will just give a brief recap. So, last time we talked about this free energy of cavity formation, and the reason we talked about cavity is we were looking at when we were looking at your putting hydrophobic solute in water, how would you put it. So, there are two ways, right. Two ways means two steps. The first one is you actually form a cavity. So, when you form a cavity, what happens is you take this solute, you put it in water, you are forming a cavity, that means you are moving the water molecules apart. And the next is, after you form a cavity, the solid molecules reorient in response to the solid molecule you have put in. Okay. So, this one was the free energy of cavity formation, and it said that your free energy of cavity formation is much higher in water than your liquid alkanes. So, this is what the conclusion was, and the cavity formation energetics showed a very unique thing. What it showed was that your energy of interaction, which is your van der Waals EA, was typically similar whether you consider water or a neat alkane. But what was really the driving force behind the effects you see was this change in entropy, which is negative in case of water, but positive in case of your alkanes. So, these were the observations, and the fact that EA was the same, it just implied that the van der Waals interaction energy is similar for both water and the alkanes, right. And then we were talking about why is the work of making a cavity in water so large. So, there were two reasons. One was the small size of the water molecule. We told something about scale particle theory, not that you have to worry about what scale particle theory is, but the essence is that when you put a solid molecule in water, then whatever configurations water had before, because of the solid molecule, the other water molecules cannot take that same place where the solid molecule is. That means the solid molecule, the hydrophobic solid molecule, or this organic non-polar solid molecule, is excluding the water molecules from the space it is occupying. Hence, the water molecules undergo a lot of reduction in configurations, which is essentially entropy, and hence the entropy decreases. That is why you see a decrease in entropy, right. But there was also another thing which was more enthalpic, which is the cohesive energy density, and the cohesive energy density is kind of a cohesive force which keeps all the water molecules together, and this cohesive energy density is by far the largest for water. Thus, there are two barriers to putting in a non-polar solute in water. One is the cavity formation, which was like this SPT, the scale particle theory, entropic in origin, and the other one is your enthalpic in origin, which is your cohesive energy density, right. This is and this was the last point we had actually started to discuss. So, I will again talk about this in a little more detail. So, let us look at these two panels now, figure panels now. So, on the left you have something which is called a neat phase to water. This is what the panel is referring to. Now, what does it mean? What it means is, again we are doing two experiments. The experiments are like this. We are taking neopentane, we have a neopentane, neat liquid neopentane, right. We are taking the neopentane molecule out from neat liquid neopentane, taking it out and putting it in water. That is what the neat phase to water means. That means a neat neopentane phase to a neopentane molecule being put in water. That is the neat phase to water. And the right side says gas phase to neat phase. It means that you take a neopentane molecule which is in the gas phase, you take it and put it in liquid neopentane, which is the neat phase again, right. So, this is why it is the mixing thermodynamics. One is you are mixing in water, the other one is you are mixing neopentane in neopentane, but from gas to neat state, right. Now, focusing on the left hand side panel, let us look at this. You see on the top is your delta mu, right, this delta mu 0. When you are looking at delta mu 0, what happens is, you see how delta mu 0 moves as a function of temperature. It kind of starts from here, then goes on increasing, and finally later you see there is a certain decreasing trend, but you do not see that. That is where the curve ends. Now, look at what happens for delta H 0. For delta H 0, you see this. This is how the line goes for delta H 0, starting from here. It goes like this. It has a huge slope, right? It is pretty steep. The same thing happens for delta H 0, right? This also starts from here and goes with a kind of a steep slope. But before going further, there are two more important things. One is, you look at these temperatures, TH and TS. What does this refer to? The delta H 0 line, which is your enthalpy change, crosses the 0 energy at TH. That means TH refers to a temperature where your change in enthalpy delta H is what? 0. So, now you think about this. If your delta H is 0, remember what delta G is or delta mu 0 is. It is equal to delta H 0 minus T delta H 0. But at TH you have already said what? At TH you have already said that your delta H 0 is equal to 0. Then what is your delta G 0 essentially equal to? Minus T delta H 0. Hence, at this temperature, which is, you see this TH is at a lower temperature, right, close to room temperature 25-30. That means, at the room temperature, whatever change in free energy you see is not enthalpic in origin. What is it? It is entropic in origin, because your delta H 0 is equal to 0. Now, you slowly move over, you see this delta mu 0 is slowly curving out, you slowly move over, you go to a high temperature side. At the high temperature side, you see delta H 0 is far over the 0 line, but what happens to the T delta S curve? You see this TS, this T delta S 0 curve, right, now crosses the 0 line of energy at a certain point, which is referred to as TS. What does this TS mean therefore? So, TS means at this point your delta S 0 is equal to 0, that means this change in entropy is 0. So, at the room temperature your change in free energy is primarily what? Entropic. When you go to high temperature, this is high temperature, this is close to 110, 112, your delta S 0 is equal to 0. So, delta G 0 is equal to what? Delta H 0. That means, at the higher temperature side your free energy change is primarily what? Enthalpic, right, it is not entropic. Is it clear? So, this is the take home point of this figure or of this diagram. Now, take the same thing and look at, keeping the same thing in mind, look at what you have on the right hand side. The right hand side again is a gaseous neopentane molecule being put in neat liquid neopentane. What do you see? For one thing, your delta mu 0 is negative, right, that means it is a favorable process, right. You are dissolving neopentane gaseous in liquid neopentane, obviously it is a favorable process. But more so, look at the slopes of delta H 0 and T delta H 0. Are the slopes as steep as you had in the left panel? See the slopes of delta H 0, in this case the slopes of delta H 0 and the slope of T delta H 0. The slopes are very small. The slopes are very small. So, on one hand, when in water, the slopes of these delta H 0 and delta H 0 are very steep, but the same thing when you take it in neat phase, neat neopentane, the slopes are actually very small. Now, what do these slopes refer to? These slopes refer to a very important thing. Okay, but before I tell you what the slopes refer to, just quickly go through the salient features of the previous figures. So, the free energy of transferring non-polar molecules from oil into water is positive and large, right, that is what your delta mu 0 was telling you, positive and large for the left hand side or the left figure, compared to simpler systems such as neopentane and neopentane, right, that is what we saw. In cold water around room temperature, the disaffinity of neopentane for water is mainly entropic, right, that is what we saw. In cold water, TH is equal to 0, delta H 0 is, I am sorry, Th means delta H 0 is equal to 0, at Th delta H 0 is equal to 0, that means delta G 0 is equal to minus T delta H 0. Hence, in cold water your disaffinity is primarily entropic in origin. Now, you move up in hot water, the disaffinity now is primarily enthalpic in origin, because at Ts your delta H 0 is equal to 0. See, you delta, this is a Gibbs-Helmholtz equation, right, delta H minus T delta S, delta G equal to. See how when you go from one end of the temperature spectrum to the other end of the temperature spectrum, within this short range, how your dependence on the parameters changes. And this is not what I am telling you, these are actual experiments where how people have done it, and they have been actually been able to figure this out, right. So, over the full temperature range of liquid water, and for liquid water rather, from the melting point to boiling point, there is a large positive heat capacity change. And how do you know that? How do you know there is a large positive heat capacity change? We will come to that in the next slide. And next point, the curvature of the free energy with temperature can be expressed in terms of the following expressions. What is the expression? The delta Cp, this can be derived, is minus T d2 mu 0 over dt squared. So, it is the curvature is always given by the second derivative. If you would remember your quantum mechanics, remember your harmonic oscillator potential half kx squared, and what was your k equal to? Your k was, yes, k was your force constant, but it was equal to d2 v over dx squared, where v is the potential, and d2 v over dx squared is essentially what? The curvature of your curve of your well. The same thing is happening here. So, here the change in heat capacity signifies or gives you an idea about the curvature of your free energy surface, okay, which is in this case delta mu 0. Not only that, look at this one, so this is also very important, this point. The temperature dependence of enthalpy and entropy can be related to delta Cp, where delta Cp is equal to d of delta H 0 over dt, you know that, or is equal to T delta H 0 over d of t, right. Now, if I am doing T delta H 0 over d of t, what is actually what is the actual thing I am finding? It is I am finding the slope. Remember that delta H 0 line. So, the slope of the delta H 0 line, so if you go back, the slope of this delta H 0 line, is given by what? Delta Cp. And because the slope is so steep, which immediately tells you that the delta Cp also is very high, because the slope is steep. Similarly, on the right side, on the right figure, because the slope is so small, what does it mean? Your delta Cp is small, as simple as that, right. Now, the same thing happens for the entropy curve. For d del S 0 over d of t is equal to del of Cp over t, and hence here also the heat capacity figures in the slope of the change in entropy with temperature. So, what it means is, if you would ever think about putting a hydrophobic molecule like neopentane in water, you will always be getting the slopes, and the reason you get the slopes is because you always undergo a huge change in what? Heat capacity. So, that is another take home point. It is actually the heat capacity change which gives rise to the steep slopes you see in case of neopentane for water, or neopentane being dissolved in water. And but for the other case, obviously the slopes are small, that means delta Cp or the change in heat capacity is small, right. So, we have already defined these two characteristics temperatures. One is Ts, it is the temperature where the entropy of transfer is 0, and Th, it is the temperature where enthalpy of transfer is 0. Now, if you would be doing some quick thermodynamics, so if you go back to this slide, and then what I can write is, I have delta Cp is equal to d delta H 0 over d of t, right. I have this. So, what I can now do is, I can say that okay, d delta H 0 is equal to del of Cp d of t, and then I integrate. I integrate between two temperatures, say the lower temperature is T1 and the higher temperature is a certain temperature T, right. And if I now expand this, so what should I get? I should be getting delta H 0 at a certain temperature T minus delta H 0 at a certain temperature T 1 is equal to delta C p, then I can write T minus T 1. What is the assumption here when I do this? Right, that means delta C p is constant and it is, as you said, independent of temperature. And especially for protein folding, the range of temperature between which we study actually the proteins folding unfolding, this assumption is not a bad assumption, right. So, having said this, we can reframe this or we can rewrite this as delta H 0 T is equal to delta H 0 T 1 plus delta C p T minus T 1. Okay. Now, the same thing can be done with delta S. So, let us do it for delta S. So, what for delta S we will have is, say for delta S 0, if I do it for delta S 0, I should be having delta C p is equal to T S 0 over d of t. And this we know. We do the same transformation, we say that d of delta S 0 is equal to delta C p by t, then d of t, and we integrate again as before. Now, we integrate between two temperatures. The before we took T 1, now we take T 2 and we are going to T, right, and hence you can further write delta S 0 T minus delta S 0 T 2 is equal to delta C p. Now, what should I write here? Natural log T over T 2, right. So, this is the other expression. So, now from this expression I can easily take delta H 0 T 2 on the other side and just get very similar to what I got for delta H 0, right. And now, you can understand if I have the expression for delta H 0 in terms of delta C p, similarly for delta H 0 in terms of delta C p, because you can see in both the cases delta C p plays a very prominent role, right, because it figures, then I can easily write, which obviously you will do, delta G 0 which is equivalent to delta mu 0. So, delta mu 0 is equal to delta H 0 minus T delta S 0. So, this you can easily figure out what it is. But you will see it is given for you in the next slide when I go through the slide, but I will do a small change in symbolism. So, when we talk about the next few slides, what you will see is delta mu 0 is now being represented as delta G 0, delta H 0 is now being represented as delta all caps, and delta S 0 is being represented as delta S 0 or delta S. Okay. It is just a small change in symbolism, that is it, right. All these things you know. So, let us go forward and see what important thermodynamic equations we have. Now, look at these equations. The first one we have derived, the second one we have also derived. The only thing again is there H was small, whereas H naught, where we are just taking H, it is easy to put in the standard states, that is not a big deal, right. And then you have delta G, and you can see this is the final expression for delta G T, that is the final expression for that. So, there are two reference temperatures, there is a reason why we took two reference temperatures T 1 and T 2. I did not take T 1 in both the cases to start with. Why did not I take that? Can someone tell me? Why did we take two reference temperatures? We just did it. What did we do? When we had that figure, What were the two temperatures where changes were going to 0? One was Th and one was Ts. So, that is why we have two different temperatures, T1 and T2. So, when we will consider delta H0, possibly we will consider Th. When we will consider delta H0, we will consider Ts to be equal to T2 and Th to be equal to T1. So, let us see how these come out. So, these are the alternative forms. The expression you have here is the most general form. You do not know what T1 and T2 are, but you have just derived it. You go to the next one. Now, you see, okay, let T1 equal to Th and T2 equals to Ts. This is the most simple, right? If T1 is equal to Th, then what happens to delta H0? 0. If T2 is equal to Ts, what happens to delta H0? 0, right? So, when T1 is equal to Th, this delta H goes to, see, when T1 is equal to Th, this delta H goes to, the first delta H goes to 0. When T2 is equal to Ts, the delta H goes to 0. So, what are you left with? Only the last term, and that is what you see out here, where you have made the small transformation that T1 now is equal to Th and T2 is now equal to Ts. That is what you have done. But this is just one, and you know this is a very simple expression you have got. Now, I can do this. I can say that let both T1 equal to T2 equal to Ts, or let both T1 is equal to T2 equal to Th. And you know I can have this. These are just arbitrary reference temperatures. It does not matter what I take. And if we do that, I know this is how it comes out. So, if T1 is equal to T2 is equal to Ts, then you immediately know at Ts your delta S would be 0, and hence you see there is no delta S term, the delta H stays. Similarly, when T1 is equal to T2 is equal to Th, you know at Th delta H is equal to 0. So, the delta H is equal to 0 term, or the delta H term drops out, and you get this. So, depending upon what you want, how you want to look at it, you can use either of these expressions. It does not matter, because all these expressions are derived from the same general expression, delta G is equal to delta H minus T delta S. That is where it derived it from. Okay. There is no further significance attached to it. It only tells you that under the given conditions, say T1 is equal to Ts, T2 is equal to Th, and all these things, then delta G can be expressed in these forms. Right. Now, the next slide gives you some thermodynamic data. What it tells you is, it gives you the transfer thermodynamics for neopentane. And when I am talking about the transfer thermodynamics, here what I mean is it's a little bit different. What this is, you have neopentane in the gas phase, and you do two things. Neopentane in the gas phase goes to neopentane in water, neopentane in the gas phase goes to neopentane in neopentane, and that is why you see in the table you have water, right, and then you have also the neopentane. So, the first one, look at this, the enthalpy, the entropy obviously is negative, but look at what is the most striking feature you see is, look at the last column, delta Cp. The delta Cp for neopentane being dissolved in water is how much? It is so high, 363. Compared to that, how much is the same for neopentane in neopentane? Only 38. So, now you can imagine why the slopes were so steep for neopentane being dissolved in water as compared to neopentane being dissolved in neopentane. It is just because this delta Cp is so high. So, this is a characteristic feature. A characteristic feature is, if you would be having a non-polar solute, the moment you dissolve the non-polar solute in water, you would be encountering what? A huge change in heat capacity. Why is this relevant? Why do you think this is relevant? This is relevant because when you start unfolding proteins, what happens? When you start unfolding proteins, your hydrophobic groups start getting exposed to water. If your hydrophobic groups are starting getting exposed to water, the same thing is happening here, right? So, hydrophobic groups are essentially non-polar. If they start getting exposed to water, that means there would be a large change in heat capacity, and it is proven that protein folding or unfolding always undergoes or is always associated with a pretty decent change in heat capacity, and this exactly falls out from whatever discussion we had up till now. It just makes sense, right? Because if you are going to have it for a single non-polar solute being dissolved in water, you think about a protein having so many hydrophobic R's, and when you are opening them up, all of these would be adding up, and hence you would be getting a huge change in heat capacity. Is it clear? So, this is where the relevance is. Now, we will discuss about this protein thermodynamics more in subsequent classes, but I just thought we would try to connect this neopentant dissolution with protein folding or unfolding. Okay. So, now this protein unfolding thermodynamics will not do much, but I will just tell you what the major difference is. Two things in the protein unfolding thermodynamics, look at this delta H and T delta S change, they are still very steep. They are still very steep, possibly more steep than what you had seen for neopentane in water, which means that obviously because they are steep, that means there is a large change in heat capacity, right. That is what we just discussed. So, as I said, steep slopes indicate large positive change in heat capacity. Now, what we are looking at is it is a protein unfolding free energy. So, this see this delta G, what we are looking at is this one, it is delta G is equal to delta G U minus delta G F. What does U stand for? Unfolded state, F stands for the folded state. We are calling it protein unfolding free energy because when we are unfolding the protein, that is the free energy that is associated with this unfolding. We are not looking at the reverse. Okay. So, now you see what happens, this delta G actually has a certain curvature, right. It is not a straight line, this delta G has a certain curvature associated with it. Why do you think this curvature is shown as it is? That means the curvature, so delta G, the curvature actually goes something like this and comes down, this is your delta G. Why do you think it goes through a curvature like this? Why does it show a positive curvature first of all? See, we are still, what about the temperature? The temperature is still room temperature. At room temperature, if you would take a protein, would you expect it to unfold? At room temperature, see the temperature is not very high. Depending upon the protein, say I am taking a pretty stable protein, a protein which is easily soluble in water, and it maintains its structure at room temperature. Then if you are going to try to unfold the protein at room temperature, obviously the unfolding free energy would be positive because it is thermodynamically not spontaneous. You cannot unfold the protein just like that at that temperature. You have to apply some external agents, say denaturing agent or whatever. But just based on temperature, that process is not thermodynamically spontaneous, and that is why you see delta G goes to the positive because it is unfavorable. Now, there is one more thing, this we will discuss later, but see it does not stay positive. That means when you go to higher temperatures, it goes to the negative, and also when you go to lower temperatures, it goes to the negative, right. Do you know what happens when delta G is equal to 0? What does that signify? Any ideas? Yes, that means K is equal to delta G, well let me say delta G 0 is equal to 0, I mean delta G 0 is equal to minus RT ln K, delta G is equal to 0, right. Now, this gives your equilibrium constant. Okay. What is the equilibrium constant between? It is between your protein unfolded state and the protein folded state, right. Remember this, I will not talk about this more right now, but remember this when we talk about protein stability, right, actual protein thermodynamics, this is very important. You know, when you fold or unfold proteins or even DNAs, RNAs and all these things, there is a certain temperature known as Tm, right, it is a midpoint temperature, it is a thermal melting temperature, right. So, at midpoint at the Tm what happens? Half and half. So, K is equal to 1. What happens to delta G 0 then? 0, right, right. So, now you can understand why delta G would be crossing 0 at two places. If you are going to increase temperature, then obviously you know that at a certain high temperature it would unfold, that means K would be equal to 1. So, that is why you see this higher place where the protein unfolds or DNA unfolds, say in this case we are talking about a protein. But isn't it surprising that when you also start going to low temperature, the protein is also going to unfold? Do you know what this is known as? See, one is if you are going to high temperature, protein is going to unfold, it is called heat induced denaturation or simply denaturation. But when you are going to also the cold side, the protein is also unfolding. This is referred to as cold denaturation. That means you are denaturing a protein in the cold, right. But anyway, that is just the point I wanted to make. But keep these things in mind, we will discuss about this more later. Now, there is one more aspect. What do you think is the major difference? Do not talk about delta G, but what do you think is the major difference between the figure you see out here for a protein and the figure you saw for neopentane in water? Okay, let me go back to the figure. Difference in TH and TS. There you go. See, this was neopentane in water. Look at the difference between TH and TS, the gap. What is this? This is huge, right? Now, you do the same thing and you come to a protein. What happens? The TH and TS are very close to each other. Okay. Now, why would this be? Why would this be? Can you reason out? The reason is actually given to you in the next slide, but I do not want to go to the next slide. Tell me, what is the major difference between dissolving a neopentane in water and trying to unfold a protein in water? It is the same thing. Neopentane, if you would dissolve it in water, that means you are taking a hydrophobic molecule and putting it in water. You are unfolding a protein, you are doing the same thing. You are exposing the hydrophobic groups to water, it is essentially the same thing. What is the major difference between a protein and neopentane, apart from the fact that one is neopentane, the other one is a protein? Many different interactions are present, sure, that is one. Many electrostatics and all these things are present, which you do not have in neopentane. There is one more thing. Remember, this is something we discussed in the very first class. Delta G is equal to delta H minus T delta S. What happens when you change? The entropy. The entropy plays a major role, right, because now you are making it more and more flexible, right. But think about a neopentane. Would you see any entropy change out there? None, right, because neopentane you take here, you take there, is the same thing. This neopentane does not undergo any folding unfolding, it is just neopentane. So, that is why this TH and TS, they come very close to each other, the gap is so small in case of a protein. Okay? And there is one more thing, is it clear? So, essentially that is what it says at the bottom, TH is almost equal to what? TS, right. So, that is what it says. How is the protein unfolding different? So, free energies of protein unfolding per unit nonpolar surface area are much smaller as compared to transferring a nonpolar solute to water. Number 2, for small solutes, TH and TS can differ by as much as almost 80 degrees Celsius, that is what you observed for neopentane, that was the solute. But for proteins, TH is nearly equal to TS, evident from this figure. And the reason being, proteins undergo large changes in conformational entropy, the same obviously is not there for your solute neopentane. Yes, you are also right, electrostatic interactions and all those things are also present, but delta S is the single most important factor, because you undergo such a large increase or decrease in delta S when you do this protein folding unfolding process. Right, this is one more thing that I need to tell you, which is, now what I have done is we have zoomed into this delta G curve. You can see this curvature. So, this is essentially a delta G. So, this let me tell you. So, this is essentially your delta G, this curve. Okay. See, when you in this figure, it was not very evident, but what I have done is I have just zoomed into this portion, and you look what happens. You see delta G undergoes a maximum. Where does it undergo a maximum? It undergoes a maximum. So, look at this point. Look at this point. So, delta G is undergoing a maximum at this circle point, and what does this circle point correspond to? It corresponds to TS. Hey, what does this tell you? This tells you where the entropy of transfer is 0, your delta G is actually at its extremum, which in this case is a maximum. Does it make sense? Well, thermodynamically it does make sense, right? Why? Well, it says here the Gibbs energy difference between the folded and unfolded states of proteins is maximum at T is equal to 0. That is, at that temperature wherein the entropy difference is 0. How does it make sense? You know this, dG is equal to what? VdP minus SdT, if you would go back to your thermodynamics, right. So, del of G over del T is equal to what? Right, and then del of del G over del T would be minus delta S, right. So, essentially what you are looking at? You are looking at is the slope. So, that means the slope of change in free energy with temperature gives you entropy with the proper sign. Hence, if this slope is going to the maximum, or this delta G is going to the maximum, what will happen to the slope? It is 0, and that is why your delta is 0, is not it? Because your dy over dx at any inflection point is going to be 0, it is extrema, right. The same thing is happening here. The delta G is maxing out there, and where does it become maximum? It becomes maximum where the entropy of transfer is essentially 0. That is for the link, and that is what, if you would remember, I did not tell you at that time, you also saw it, if you would look at it again, let us see here, you can see this Ts, look at this Ts here, and look at the delta G out here, there also delta G is kind of maxed out, but we do not see what happens later. Okay. So, I think this is typically what I had to discuss about hydrophobic effect. Just last one point, how would you actually rationalize at the molecular level this large increase in heat capacity? How would you rationalize? So, the rationalization can be done by many models. One of the models which still stand and which kind of gives you a very logical interpretation of what is happening is what is referred to as the iceberg model, right. What does the iceberg model tell you? You look at this, you have a solute which is your neopentane, you are trying to dissolve it in water, right. You have not yet dissolved it in water. Okay. I am looking at the left hand side, right, I am looking at the left hand side of the arrows. You can see water has its own tetrahedral hydrogen bonding network, you have not disrupted it, right. Now, the moment the solute is disrupted in water or put in water, what happens? The solute is going to occupy a certain place, the solute is non-polar. So, the water molecules will not waste their hydrogen bonds by trying to bond with the solid molecule. Instead, what it will do, or what will the water molecules do? The water molecules will actually bond to themselves, right, but they will bond to themselves such that they avoid the solute which is in the center, and they form kind of a hydrogen bonded shell which is called the first solvation shell or solvation shells around the non-polar solute. So, this is what you are seeing out here. So, you look at this, here you can see the water molecules are hydrogen bonded to each other, right, surrounding the solid molecule. Now, this is at cold water means room temperature, 15 degrees, 20 degrees, 25 degrees, whatever. So, in this case your water essentially is what? Ordered. Also energy is low because the temperature is low, right. It is ordered, so its entropy is low. Okay. And the reason again water is doing it because it does not want to waste its hydrogen bonds, it wants to utilize its hydrogen bonds to the maximum, and it can do so by hydrogen bonding amongst themselves, right. Now, why is it called the iceberg model? It is called the iceberg model because you remember in ice what happens, it is an anomalous expansion of water. When you go to ice, in the solid form, ice also has some sort of a tetrahedral order, right. So, it is not exactly an ice, but it is kind of an iceberg model, it resembles the kind of order you tend to have in ice, only that is the similarity, that is why it is called an iceberg model. Do not think that the same kind of coordination you have in ice is going to be maintained here, it is not going to be like that. Okay. So, this is clear. Now, think about this case, high temperature. So, this is I am marking by the arrow, it is a high temperature case. What happens at the high temperature? You are putting in energy, right. Now, if you are going to put in energy, what will happen? You will try to disorder the water molecules. Now, what will the water molecules do? So, water molecules will try to assume many different orientations. That means, at cold water the water molecules were ordered, is not it? In cold water the water molecules were ordered around the non-polar solute. You pump in energy, what happens? It goes towards disorder, more disorder, because it has to respond to this change. So, that means when you are in cold water, and let me write it, I am saying too many words I guess. When we are in cold water, when we are in cold water, we can say we are in a low entropy and low energy state. Now, when we go to hot water, that means when we increase the temperature, we go to a high entropy, and also it should be high energy or high enthalpy, isn't it? Why? Because when you are pumping in energy, and where does this energy going? This energy is going in breaking the whatever hydrogen bonds you had formed. So, this energy is actually breaking hydrogen bonds, and hence you have the system has actually more energy. So, entropy obviously corresponds to delta S, and you know that delta S is increasing, entropy is increasing. Also, high energy means your enthalpy is increasing. Now, what is the relation between delta H and delta Cp? Is the slope. That means we knew that d of delta H over d of t is equal to delta Cp. So, if my delta H has to increase, then delta Cp has to increase. The same thing happens for what? Entropy. What was entropy? D delta S over dt is equal to del Cp by t, right. So, d delta S over d of t is equal to del Cp by t. So, both of these are increasing, and both of these have a strict delta Cp dependence, and because this is increasing and because you are looking at the slope or the rate of change, it just figures that a delta Cp should also change, be positive and change by a huge amount, and hence this is the molecular interpretation behind why you see a large change in heat capacity, because your water molecules essentially go from an ordered state, low energy state, to a disordered state and high energy state. Order to disorder, delta S is positive, low energy to high energy, delta H is positive, and hence delta Cp has to be positive, that means delta Cp has to increase. So, this is the molecular nature, that means at the molecular level what is probably happening in solution around your non-polar solute, or even your hydrophobic side chains of your protein when you are actually unfolding it. So, if you would ever look at, we will look at it later as I keep saying, but if you would ever look at protein unfolding thermodynamics, you would always see a huge change depending upon what protein you have in heat capacity. That means a change in Cp or the delta Cp would be high just because of this reason. Is it clear how it is coming around? Think about it, it is actually very logical, because both delta H and delta S actually depend upon Cp, or vice versa. If delta H and delta S are increasing, then delta Cp has to follow suit, increase. That is the only way how delta H and delta S can increase. So, this is typically how at the very basic level or the very molecular level, molecular terms, you can think about increase in heat capacity, right. So, as it says, at room temperature the water molecules that surround the non-polar solid molecule occupy a state with low entropy and low energy. The water molecules are ordered. As temperature increases, water molecules cover a wide range of orientations, because it has to respond to the change in entropy, getting disordered. In this process, hydrogen bonds are broken between water molecules, leading to increase in enthalpy, that is essentially energy, and hence you see a change in Cp, increase in Cp. Okay, so that is what we just said. So, thus as is obvious from the discussion in the previous slide, increase in enthalpy and entropy will lead to a positive change in heat capacity, right. So, given a situation, given any problem, the idea is that you should be able to explain without any equations at the molecular level physically what is happening, provide a physical picture, and I hope this helps you do that, and this is how you should be able to relate thermodynamics. See, this is thermodynamics, right. All these things you have known, you have read when you are doing your first laws, second laws and all these things, and this is where you see they are being used. There is actually a practical application of your thermodynamic principles, whatever you knew you are applying out here. So, this is all what I thought I would be telling you about hydrophobic effect. Its actual application to protein folding, I will take it up a little bit more when I do talk about protein thermodynamics. I just do not want to make the jump here right now, because I still have one more thing to cover in forces. We had covered electrostatics, right, which included different interactions, charge, dipole, dipole, charge, dipole, van der Waals. Then we went to this hydrophobic effect, right. But there was one thing also, which is hydrogen bonding, and hydrogen bonding is important because your secondary structures, alpha helix, beta sheets, we have seen before, they are all hydrogen bonded, right. Secondary structure is actually symbolized alpha helix by this intrahelical hydrogen bonding, or beta sheet by the intra-strand hydrogen bonding. So, hydrogen bonding has to be able to play a significant role in providing stability or governing the protein folding thermodynamics. Okay. So, the next topic is hydrogen bonding, and how do we look at it? So, let us think about hydrogen bonding, its contribution to protein folding thermodynamics. So, what it says is hydrogen bond formation in a protein does not bring about a net gain in the number of hydrogen bonds formed. Why does it say so? It says so because the groups involved in hydrogen bonding were forming hydrogen bonds with water in the unfolded state. So, that means when the protein was not folded, whatever groups were forming hydrogen bonds, because what are the groups which form hydrogen bonds? It is not a hydrophobic groups, right, it is the NHCO and all these things, your salt bridges and all these. So, when they are open, you had water molecules, they were polar, so they could easily hydrogen bond with water, right. So, you actually do an exchange in hydrogen bonds. Initially, when the protein was unfolded, the polar groups NHCO, these groups, they were hydrogen bonding with water, no problem. Now, when you fold the protein, depending upon the orientation, depending upon the type of fold you have, it will start hydrogen bonding, forming hydrogen bonds within themselves inside the protein, right. But so, where does the stability come from? The stability comes from the difference in strengths of the aforesaid protein water and protein hydrogen bonds, right. That is what is going to be one of the factors which will be governing the change in energy or the gain in energy you have when you go from a folded protein to an unfolded protein. That is one. See, this how you think about it, it is actually a major issue, right, because even before they were forming this intrahelical or intrastrand hydrogen bonds, they were actually happy forming the hydrogen bonds with water. Only that the hydrophobic groups were probably not very happy sitting in water, so they had to come inside. Next, now hydrogen bond strength will not be universal everywhere or not be the same everywhere. Now, why do we say that? We say this because the hydrogen bond strengths will depend upon the polarity of the immediate environment. That means you think about this, suppose you have a hydrogen bond in the inside of a protein, right, where we have a protein core, we have a hydrogen bond. Now, inside the protein core is essentially non-polar. Remember, hydrogen bond is essentially electrostatic in nature, right. If you consider electrostatics, all of those had a term d, the dielectric constant at the numerator, remember the d, okay. So, that means higher the dielectric constant, essentially the dielectric constant will be able to shield the interaction between the corresponding charges, but when you are inside a protein core, what happens? Your d is anyway low. So, that means the hydrogen bond strength out there should be higher, because if it is an essential electrostatic force, you are not being able to shield those two from each other that much, right. But if you have, say, surface hydrogen bonds or somewhere else, then those hydrogen bonds, what will happen? Now, they can interact with water, hence d will be higher, and thus the bond strength essentially will be lower. Now, this is exactly what is being shown here. You look at this. So, if you take let us start from the soluble protein, which is the green one, let us start from here. The soluble protein, you are looking at surface hydrogen bonds. Surface means on the surface of the protein you have these NHCO groups or these polar groups, they form hydrogen bonds with water, and the average distance is, the mean HA distance is 2.08 angstroms or 2.1 angstroms. You take the same thing, you go to a soluble protein with buried hydrogen bonds. Now, what you are doing is you are looking at hydrogen bonds, but this time you are looking at the buried portion of the same protein. Now, what is happening to the bond length, it decreases. That makes sense, right? If it is going to the buried portion, there your d will be lower, hence it will not be able to shield the corresponding charges, and hence the bond will be stronger. Hence the strength of the bond is signified by a lower bond length. So, it is about 2.02 angstroms. Now, you go to the membrane protein buried hydrogen bonds. You have taken the protein and you have taken a membrane protein and put it inside a membrane. See, the buried hydrogen bonds are buried hydrogen bonds, they are in the core. Whether you take a membrane protein or a soluble protein, the core is always hydrophobic. Hence, that is why it is logical that they would be similar. But look at this, if you take the membrane protein and surface hydrogen bonds and compare the soluble protein and surface hydrogen bonds, you see there is a remarkable difference. Why is this so? This is because when you take the membrane protein and surface hydrogen bonds, remember the membrane proteins are sitting on your membrane, right? The surface hydrogen bonds, the way they point is the surface hydrogen bonds actually point towards the interior of the lipids, and when they point to the interior of the lipid molecules is essentially what? Hydrophobic. And if the lipid molecules are hydrophobic, again d is very low out there, because remember in a protein core you can have what? You can have polar amino acids, but in the lipid core you cannot have polar amino acids. Lipids are just lipids, you know, hydrocarbon chains, hydrocarbon tails, you cannot have anything else, and hence that is why the d is the lowest out there, and that is why you see the bond length is also the lowest, because hydrogen bond is the strongest out there. Okay. So, tomorrow what we are going to look at is, can you prove this? Can you actually prove this? This is called contextual dependence of hydrogen bonds. That means you are looking at the hydrogen bond, where is it placed, and depending upon where it is placed, that means its immediate environment, which is called the microenvironment, how would the hydrogen bond strength differ? Can you actually prove it? See, it is easy to understand, but proving in case of a protein is not so easy, and that is what we are going to discuss tomorrow. Okay? And that will be essentially a last topic for our forces in protein folding. And the reason I am telling you we spend so much time is, if we do not understand these forces, see these forces are in case of protein folding, but you think about the forces, these forces are universal. Whatever forces we are taking proteins as an examples, whatever forces we are talking about, these forces we know, and wherever you go these forces are not going to change. The magnitude might be changing, but the nature of the forces are not going to change, they are going to remain the same, and that is why knowing those in a little more detail is actually I think very important. Okay? So, tomorrow we will start with hydrogen bonds.